So for the graphs of y equals tan x, cotan x, and secant x, let's go over what these things look like. We already took a look at what sine looked like and cos looked like. You can find these on page 3 and 5 of the handouts, but what I'm going to do now is I'm going to talk about what tan x looks like. So for the equation of tan x, you need to realize that tan x is equal to just sine x over cosine x. Remember, I talked about that in the past lesson. So now, because it's equal to sine x over cos x, it's bound by the rules that we studied for functions that were made of quotients of functions. So for this bottom portion of our function, we have our x values cannot equal, well, cos of pi by 2 is 0. So can't be that. It can't also be 3 pi by 2. And it goes on forever. And it goes on in the negative direction as well. So the vertical asymptotes for something like this is x is equal to n of pi divided by 2, where n belongs to integers. So for this basic graph, you have something that looks like this. And you have all of these vertical asymptotes at the following. We have it at x equals -1/2, x equals 1/2, x equals 3/2, just like we had calculated before. Now, if we had done the analysis as we got close to this vertical asymptote here, our value would increase constantly. Okay, and then as we went from as we approach from the left side of this asymptote here, you'd notice that it would go down to -infinity. You knew that at pi, our cosine was equal to 0. Tan was equal to 0. All right, that's basically it, right? The only thing that's left to tell you is that the period for something like this is always, so the period for something like this is always pi, otherwise known as 180 degrees. And that thing gets repeated over and over and over again, where we always go and draw this basic graph here in the center. And we always draw our vertical asymptotes to set it up, and then we continue to repeat that same pattern for infinity, going forwards along the x-axis and backwards along the x-axis. Now we'll go take a look at what cotangent would look like. So remember that y is equal to cotangent of x is the same as saying y is equal to cosine of x over sine of x. So remember, it's just the flip of the tangent. So let's do some analysis on the denominator. So we'd have to find out where sine of x is equal to 0. And for us, sine of x only equals 0 when sine is 0, pi, 3 pi, no, 2 pi, 3 pi, and so forth, okay? It also goes back as well in the same pattern. So in this case, for the denominator of this equation, the vertical asymptotes are going to be the following. Now, when we do our analysis, you're going to find out that the vertical asymptotes for our function y is equal to cotan x is going to be n pi for x. So in essence, we have something that looks like this for our graph. So for our graph, we have y is equal to cotan x. It looks very similar to to what we had before, except our zeros occur at 1/2, 3/2, and -1/2, and it goes on forever. So we have our zeros is equal to n pi over 2, and n is for all integers. And here is the cool part. It's exactly like what we drew before, but this time we have our vertical asymptotes are just shifted to the left a little bit by 1/2 pi, and then it's the swoop that we had from tan, which went from here to here, is now going this way on our graph, and that's it. Okay, and you'll notice that our vertical asymptotes are -pi, 0, pi, and it goes on forever, like I said right here. All right, so now let's go and explore the graph of y is equal to cosecant of x. So for this problem, we're going to actually have to take a moment, and we're going to have to look at the fact that our original graph of y is equal to cosecant x is really just 1 over sine of x. Now, because it's 1 over sine of x, it has some properties that we can use. So why don't we go and draw y is equal to sine of x on a graph. So for a basic graph of y is equal to sine of x, it starts at 0, it goes up, and then goes up to 1 at pi over 2, and then goes down, and then up, and then down, and then up. Okay, so the only thing that we have to worry about is where our zeros are. So if I was looking at this graph, this equation that I have for my graph of y is equal to 1 over sine x, this tells me that my vertical asymptotes are going to be right here. And it just happens that our vertical asymptotes are literally going to be anywhere where we have our sine, our original sine graph equaling 0. So in this case, our vertical asymptotes are going to be x equaling n of pi for n being integers. Okay, so that's what our vertical asymptotes are for each one of these things. So for this one here, I have x equals 0, x equals 1, x equals 2, blah, 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 pi, and then this is 2 pi, and then this is 3 pi. And the same can be said on the other. So now we've got all our vertical asymptotes. So exactly what happens when we take 1 over the sine of something? Okay, so we know at this point here, our value of sine is 1. Okay, so for this specific point here, we have a sine of value of 1. Now, if we went and took a look at our asymptotic analysis, i.e. we went close to, we go close to this point, close to this axis here, this vertical asymptote, here's what happens. As I get closer for sine to 0, when I take 1 over that value, my value becomes immense. So our graph looks like this on this side, and then the same can be said for this side. Now, when we go and take a look at -1, the same thing happens on this side. And now our graph does this. And the same can be said for this side and this side. So for our y is equal to cosecant of x, we have our graph looking exactly like this. So if we wanted to graph the other thing, you can do that as an exit task for your class. So here's the best part about it. We know that our y values go on forever, but our y values are greater than -1. Y values are going to be y such that y are greater than or equal to -1. No, not -1. Greater than or equal to 1, and also less than or equal to -1. And that is the range of y. We could also say the domain of y is all the x's such that x cannot equal, well, n of pi, where n belongs to integers, and that's it. Oh, and x belongs to real numbers. Okay, so this basically is what our cosecant graph looks like. So what I want you to do is I want you to graph y is equal to sine x for an exit task. Okay, so we have all that information about our range and our domain for this thing. Now, the only thing that I want you to remember is that this thing has a period. Our period is actually from here. It's actually this and this repeated over and over again for our function. So you'll notice that our period in this case is actually 2 pi, also known as 360 degrees. Okay, and in that period, there is always 3 vertical asymptotes at the beginning, at the middle, and at the end. All right, so now you're going to go and do that exit task for me. So for your exit task today, what you're going to do is you're going to graph y is equal to secant x, and you're going to note that for secant x, it's equal to 1 over cosine x. So when you graph that, you're going to graph it with graph this. Graph y is equal to cosine x, just like we did before. Okay, but use dashed lines. And then go and proceed to graph y is equal to secant x. So now on to the lesson. You know what? I want the Lubuntu LTS instead. You know what? Yeah. You know what? We'll do it. Let's cancel this.